In the sciences, there's two ways to find something out, generally. One is you can measure it yourself. The other is you can see what's already known and figure things out from what's already known. And Hess's law is going to fit in that second category. Hess's law lets us determine enthalpies of reaction without actually doing the experiment ourselves. Now, because we know that enthalpies are going to be path independent, we can add any combination of known reactions together. And as long as everything cross-cancels through all of the reactions that we put together to give us the reaction we actually care about, we'll be able to determine the enthalpy of reaction without actually conducting that experiment. Now, suppose for whatever reason we can't measure this experiment in a calorimeter. Maybe we only have a coffee cup calorimeter and we can't actually work with two gases producing a third gas. Or maybe we just really don't want to deal with nitrogen dioxide being formed in the lab for some reason, or whatever reason. Instead, what we can do is we can look up some reactions. Now, what we need to do is find a set of reactions that, when we combine them, end up having these two reactants in these states of matter. The only product we want to have once we add them all together will be 2 moles of NO2 in the gas phase. Now, suppose we go look at one of those tables and we find these reactions. You can see here that I've got those two reactants, so we've covered both of our reactants with this one. But it's not giving us the right product. Notice that it's NO, not NO2. However, if we take 2 moles of NO2, we can get NO and oxygen. Wait a second here, but that one doesn't help us, does it? Well, if we reverse that reaction, notice that we'll have it set up. Also note, we still have to have our stoichiometry match up. And in this first reaction, the stoichiometry doesn't match yet. We have 1 mole of N2 plus 1 mole of O2. Now, when we flip this reaction that we know of around, remember that anytime you flip it backwards, we change the sign on the energy, because now instead of the energy being added, it's going to be coming out when we reverse it. So you can see here, I've taken those two reactions again. I have my N2 gas, I have my O2 gas, and they're generating NO. Now I've got 2 moles of NO, and notice this is going to cross-cancel, and we can do that. We're going to make something, then we're going to use it up right away. We have an extra mole of O2. We're now producing 2 moles of NO2, and if we add these two reactions together, we end up having 1 mole of N2 and 2 moles of O2, both in the gas phase, are going to yield 2 moles of NO2 in the gas phase. So what we can do now is add together these energies to give us the overall enthalpy of reaction. That's how we use Hess's law. Now, there's other ways we can do it as well. Instead of looking at actual reactions, we can also try to have an energy associated with each of these molecules, and then we can try putting them together, and we'll see that in a separate video. This video focuses on our heat summation. So that's when we're going to take different reactions, add those reactions together, and as a result, we're going to be able to determine the overall enthalpy of the net reaction for all of it. Now, there may be some tiny differences in the measured energy versus the calculated energy. But usually that's not, in fact, always, that's not going to be a sign that Hess's law broke down. That's going to be a sign that we didn't control our variables so well that it's perfectly matched for all of the different scenarios. But when we have all of our experimental conditions the same, we will actually get everything to add up with Hess's law because, I'll point out again, enthalpies are going to be path-independent functions. Now, just as a quick summary, since we're going to see a few different ways of doing these calculations, this particular approach uses pre-measured reactions.